Welcome to a new lecture on SA2, our third module, Flexibility Matrix Method. So we have learned about what is flexibility matrix. Now let's see what is flexibility influence coefficient Fij. So flexibility matrix is represented by small letter r is equal to F dot capital letter R, where small letter r is equal to displacement, system displacement, and capital letter R is system force. System force and system displacement. Small letter f is flexibility matrix. So it is nothing but a matrix that connects displacement with a force. So it is a displacement response to a force. If I apply a unit force, the corresponding displacement I obtain is called as flexibility. So flexibility is nothing but a displacement. That's what we learned. So now our definition is what is flexibility influence coefficient. Consider we are writing this in a matrix form. In the matrix form, there are n number of coordinates. We assume n number of coordinates. For example, I take a beam, it has n number of loadings. So n number of points I consider first point, first node point, second node point, third node point, fourth node point, etc. etc. So if there are n number of coordinate points, we will get a n by n flexibility matrix. So F11, F12, etc. etc. It goes on. So each term in this flexibility matrix is called as flexibility influence coefficient. So let's see. It is a displacement at I due to unit force at J. So in this case, if I take F12, it is displacement at a first position due to a unit load at the second position. So see here, it is displacement at I due to unit force at J. Now let's see the derivation of a flexibility matrix of a beam element. So as we derived for the stiffness matrix for a beam element, we are going to derive the flexibility matrix for a beam element. I consider a beam element, we are assuming only two system coordinates, that is rotational system coordinates existing in a beam. So in major way, the beam bends, right? The beam bends, that means a flexure is occurring. So we are considered or interested in considering only system coordinate as rotational coordinates or moment coordinates, ignoring the translational coordinates. So how we will derive? Let's see. First step is apply unit force at a first element coordinate. This is an element level approach. So we are applying unit force at the first coordinate point. That is, we have two coordinates, 1 and 2. We are using the principle of superposition and applying the first load only, keeping the other load removed. So first load I applied and find the corresponding values of load, that is flexibility values. For this, I apply the load. What should be the load? I am applying a unit force. That means the force is moment. Moment m is equal to 1 is applied. Correspondingly, displacements are obtained at 2 points 1 and 2. So F11 represents first point displacement due to load at the first point. F21 represents displacement at 2, displacement at 2 due to unit load at 1. Right, we have to find the values of F11 and F12, for which we will follow conjugate beam method. Conjugate beam method to find out the value of two theta values, that is slope values. So a quick recap of conjugate beam method. The slope of a real beam is equal to the shear force of the conjugate beam. That's how we study. We have to convert the real beam into a conjugate beam, and the displacement of the real beam is the bending moment of the conjugate beam. So how should be the conjugate beam's loading be? The loading of conjugate beam should be the m by ei of real beam. So let's draw. This is my real beam. I am converting it into a conjugate beam as shown. The hinge will remain as hinges in the conjugate beam, and the loading will change from moment m equal to 1 to the m by ei diagram. So what is the bending moment diagram of the real beam? At the joint A, there is a moment m equal to 1. That only exists at this point. At this point, there is no moment, hence 0 occurs. I have drawn the BMD, m value equal to 1, so 1. So I have to convert it into m by ei diagram. So m by ei diagram, that is equal to 1 by ei value, because moment m equal to 1. So find out the shear force at a point A. How you can find? We have to find the support reactions Ra and Rb. So Ra plus Rb is equal to the load. That is half this area. This total area will become my load. That is a half into L into 1 by Ei. Half into L into 1 by Ei is the area of triangle. That is L by 2 Ei is equal to Ra plus Rb. That is our sigma Fy equal to 0. Right. Now take moment about any point. I am interested in taking moment about A equal to 0. So RB into L, RB into perpendicular length L, that is given here. That is acting in this direction, minus the load. Total load is half into L into 1 by A. It is acting at a distance of L by 3 from joint A. So load into L by 3 is the centroidal distance. That will give moment about A equal to 0. Equate it as 0. Then we will get RB into L equal to L square by 6CI, from which solving I get RB is equal to L by 6CI. We already know RA plus RB is equal to L by 2EI. Substituting the value of RB there, we will get RA is equal to L by 2EI minus L by 6EI, that is L by 3EI. So L by 3EI is the support reaction at RA, L by 3EI. That is nothing but my shear force at that point. That will become the theta A at this point of the real beam. That theta A is nothing but my F11 value. Theta A is equal to RA. Right. So I have found out theta A is as L by 3EI. Similarly, theta B equal to RB. That is equal to RB is given as L by 6EI. So next is finding out the direction. Here RB equal to L by 6EI, but its a direction is opposite of the second coordinate, and hence anti-clockwise is taken. See here, the RB is producing an anti-clockwise moment, and hence it is opposite to our second system coordinate. What is second system coordinate? Look at this second system coordinate. It is clockwise, right? So RB is acting anti-clockwise, or RB is producing a moment which is anti-clockwise. So we take the value of RB as anti-clockwise. So minus L by 6 EI. Whereas theta A is equal to L by 3 EI is taken as positive, because RA will produce a clockwise moment. So that is a clockwise rotation is occurring at the first system coordinate, and hence a positive value. Okay, so we got two values, L by 3 EA and L by 6 EA. One is minus. Next step is apply unit load at the second coordinate. That is same procedure, same values we will get, but of opposite values. So apply unit load at the second point. That is, I apply a moment here in clockwise direction. The beam will bend like this, producing a deflection. So this is my F22 value, and this is my F12 value. How it get? That is a displacement at 1. Displacement at 1 due to load at 2. So F12 value, solving the same step as in the previous case, we have to apply the conjugate beam method and find out. You don't have to do that. You just can substitute the values. F12 will become L by 6 EI, and F22 will become L by 3 EI. You have to change the values. Okay. So F12's direction, it is anti-clockwise, hence a negative value is given. Whereas F22 is positive clockwise, L by 3 EI. Finally, writing the matrix, I will get it as L by 3I here, L by 3I here. A negative sign is given, L by 6i and L by 6i. See, it is diagonally given, right? So finally taking L by 6Ci common outside, I can write L by 6Ci 2 minus 1 minus 1 2. This is my element flexibility matrix. Very important. Element flexibility matrix. You have to by heart this one to solve our problems. Next is element flexibility matrix for a trust element. We are interested in considering only one system coordinate or one system coordinate or one coordinate. So I take an element axial force P is acting. So I apply a unit axial force P equal to 1. The system displaces by an amount delta L. So axial load, we know the formula. Stress by strain is equal to Young's modulus E. Stress is equal to load by area P by A. Strain is equal to delta L by L equal to E. So write it in terms of delta L equal to PL by AE. I apply P equal to 1, I get delta L equal to L by AE. So delta L is displacement. Displacement itself is called as flexibility when we apply the load as 1. So F is equal to L by A. E is the flexibility matrix for the truss element.